Okay, greetings aspiring scientists. Welcome to my video today on the bonding triangle between covalent, ionic, and metallic bonding. Here I am at school again with no classes in a cold room, but hoping just to make a good YouTube video today. So let's go to my slides. We are now in structure 2.4, from models to materials. So more talking about how bonding relates to the properties of materials that we actually work with. And I think I did forget to go over the guiding question for metallic bonding, so quickly we can do that. What determines the metallic nature and properties of an element? So what really determines whether it will be metallic is actually its electronegativity. I think that's something that I didn't really talk about last time, but I will talk about today. But once something is determined to be metallic and to release its valence electrons into a sea of delocalized electrons and have a lattice of cations, the things that determine its properties and nature are really the number of valence electrons that can be released, the charge of the cations that will be left remaining, and the radius of the ions that are left. Okay, so that leads us very nicely in today, from models to materials. So our guiding question here is, what role do bonding and structure have on the design of materials? And I think we will learn that it's pretty much everything. Bonding and structures, lead to the fundamental properties of materials. Therefore, we have to consider them when we choose what materials we want to use and design things with. So the bonding continuum, 2.4.1. So you've probably considered now that there's a kind of spectrum between ionic and covalent bonding. It's not just one or the other, but depending on the electronegativity, from zero electronegativity difference from 0 to 4 or whatever, we can have complete covalent bonds, nonpolar covalent, all the way up to highly ionic. And that forms a kind of spectrum. You could imagine a line where you're somewhere on that line. And if you're closer to ionic, you're more of an ionic bond. If you're closer to covalent, you're more of a covalent bond. But that kind of spectrum and line also exists between covalent and metallic, and between ionic and metallic as well. So if you end up with these three lines, and at each corner you have pure covalent, another corner has pure ionic, another corner has pure metallic, you'll end up with a triangle where all the lines are connected. And instead of a linear spectrum, a one-dimensional thing, we end up with three lines making a two-dimensional object, which is a triangle here. It's a plane. And your material can be anywhere inside this triangle or on the edges or on the corners, but somewhere on here, based on its electronegativity and difference in electronegativity, it will have properties of covalent, metallic, and ionic bonding. So as we have seen, many materials do not clearly have ionic, covalent, or metallic bonding 100% of each. Rather, they are mixtures. There are gray areas and things to consider in between these pure types of bonding. So we have what we call the Arkel-Ketelaar Triangular diagram. It's kind of shown here on the right without much detail, but on a basic level, you can have something that's like strongly ionic, CSF, in the top corner for the ionic corner, purely ionic. You can have something that's very strongly covalent or purely covalent, like F2 in the right corner. Or you can have something that's strongly metallic, like CS, cesium, in the bottom left corner. So it is called the Arkel-Ketelaar Triangular diagram. You do have this in your data book in section 17, page 18. But if you forget the name, I think you can often just refer to this as the triangle or triangular bonding diagram. It's usually fine. So we need to compare these types of bonding again to kind of judge what properties things will have depending on where they exist in the triangle. So things that are closer to metallic, they're going to have varying melting and boiling points because it really depends on the number of valence electrons released and the radius. If you have only one electron released in something like sodium, it has weak metallic bonding, therefore a fairly low melting and boiling point. Volatility for metals, though, is fairly low. The atoms, the cations in the lattice, don't generally become a gas very easily. They're stuck in the crystal structure. Water soluble, generally not. Again, water, a polar covalent molecule, would try to surround the metal atoms, but it can't really get in and break through the sea of delocalized electrons in the lattice of cations. They're usually in a fairly stable structure. They can't be dissolved. Electrical conductor, metallic bonding, yes. They have the sea of delocalized electrons. Those are mobile charge carriers. Electrons can move current through the metal. Thermal conductor, yes. Again, moving electrons can collide with each other and collide with the positive lattice, transferring kinetic energy and heat very quickly. Brittle, no. They tend to be the opposite. Metallic bonding favors malleability, usually. So when a force is applied, instead of cracking or breaking, they just reform a new shape. Susceptible to corrosion, though, yes. So metals, although they're fairly strong and stable, there are some reactants that will cause them to oxidize or break down or corrode. So we can say that they are susceptible to corrosion and they're fairly reactive. Again, it really depends on the metal, though. In general, though, I'll say yes, susceptible to corrosion. Then we move on to ionic bonding. What properties does this have? Melting and boiling points, high. This is a strong lattice of anions and cations that are strongly attracted to each other. You have to put in a lot of energy to break them apart. That's high melting and boiling point. Volatility is fairly low. They don't become a gas very easily for the same reasons. Water soluble varies, but I think generally we can say they're more soluble than other things. Water molecules, polar covalent compounds with positive and negative regions, can be attracted to either the cations or anions on the edge, and when enough water molecules surround it, they'll pull it off and keep it surrounded in solution that is dissolving and high solubility. Of course, we'll learn today, I think, that some of them are less soluble for some reasons, and it has to do with the bonding becoming slightly more covalent or a different type of bonding happening than pure ionic. Okay, electrical conductor. Ionic compounds generally no when they are a solid salt, but yes when they are melted into a liquid or when they're dissolved in water. They are charge carriers, they're positive and negative, cations and anions, but in the solid crystal structure they are not mobile, they cannot move, so they cannot move current around. Thermal conductor, no. There's not a lot of mobility in a solid ionic compound, so you're not going to have collisions and transfer of kinetic energy happening very well. Just each cation and anion can vibrate in place, but that's going to take a long time to transfer kinetic energy around. Brittle, yes. So they are not malleable in the same sense as metallic bonding compounds are. When a force is applied, instead of sliding, generally a crack or break in the structure will form, and you get sort of chunks or powders breaking off. Susceptible to corrosion, yes. I don't know much about this corrosion of ionic compounds. I thought, in fact, usually salts and salt water do the corroding of other things. So I don't know, might have to look that one up. But apparently in this table I generally got this information from the textbook I use, Oxford Course Companion. So I don't know how true that is, ionic compounds susceptible to corrosion. But moving on, molecular covalent, low melting and boiling point. That's because they are not in a crystal lattice so much as a intermolecular force-based solid or liquid most of the time, so it doesn't take much energy to heat them up and separate each individual molecule into gas particles. Low melting and boiling point. Volatility, for the same reason, it's high. Even at like room temperature, standard conditions, a couple molecules will gain enough energy to leave their surrounding intermolecular forces and become gases. So that's high volatility. Water soluble varies. Again, we've learned about polarity. You can have non-polar things like hexane or oils that don't dissolve in water very well. They have no attraction to water molecules. But then we have things like the polyatomic ions or ammonia, like polar covalent, that will dissolve well in water. Electrical conductor, no. So generally, these non-charged molecular covalent bonding structure things have no charge. They might be able to move around, especially as a liquid, but because they don't carry charge, they can't push current around. Thermal conductor, no. Generally, they just won't transfer kinetic energy that well. Brittle, yes, when they are a solid. Instead of being malleable, you'll just break apart the intermolecular forces and form cracks and breaks in the material. Susceptible to corrosion varies. I don't think we have a good idea. There's a huge range of molecular covalent compounds, and I guess some can corrode or oxidize or react with acids or whatever, but some will be more resistant. Covalent network then, these can have much different properties than covalent molecular compounds. So melting and boiling point of this is high. They have strong covalent bonds with several neighbors in several directions. They're not going to be breaking apart that easily. Same reason, low volatility. Same reason, water soluble. Polar water molecules might come to the edge of this, but they're not going to surround or be attracted to it. There's not charged particles in covalent networks generally. Electrical conductor, no. Things like diamond or SiO2, silicon dioxide, they don't have mobile charge carriers in the lattice, so they don't conduct. But things like graphite, they do have delocalized electrons in what's called a pi conjugated system. So they can, and graphite and graphene certainly can. Thermal conductor varies. Diamond, however, has very high thermal conductivity, almost the highest of any solid we know of, due to its ability to transfer vibrations very efficiently. Brittle, yes. Instead of sliding, we need to break the bonds. There's going to be cracks forming. Susceptible to corrosion, no. Generally, these covalent networks are very stable and stable enough that they don't do chemical reactions. They're chemically inert with, water or salts or acids or oxygen. So we can say they have low corrosion. Okay, so that brings us to some properties that we need to be able to know and define. Elastic materials are able to return to their original shape when deformed. When a force is applied, you can think of an elastic band. You apply a force, but when you release it, it returns back to its original state. That's elasticity, the property. On the other hand, plastic materials are kind of the opposite. They're able to maintain their deformed shape. So you can think of like Play-Doh or putty or even metals. These are generally plastic. You deform them, they keep the new shape. Okay. Metals, although, can be elastic as well. Depends on their structure and the amount of force applied. You can think of like a spring, right? Or a wire. You can deform that and it will usually go back to its original form, but there's going to be a breaking point where you permanently deform it. Okay, corrosion then occurs when a material is oxidized in the presence of oxygen and water. You can kind of think of this as rusting when it happens to metals or metalloids. What else? Lustrous means like shiny, so these things reflect light and appear shiny. Whatever electromagnetic waves from the visible spectrum or possibly other parts of the spectrum, when it hits those materials, they'll either reflect or immediately absorb and emit the same radiation that hit them. Very good words to remember and describe the properties of materials. So some practice. Explain the opposite trends of these tables with reference to intra and intermolecular forces. All right. So I want to look at the right side first, actually. It's more clear that as you go from bottom to top, there's an increase in melting point, and as you go from top to bottom, there's a decrease. And I think that's because these are ionic compounds. Kf, KCl, KBr, Ki. You can check the electronegativity difference between those, and it's going to be pretty high, I think, around 1.8 or higher. So what determines melting point and bond strength in ionic compounds? Well, in this case, it could be the radius of these changing anions, F to Cl to Br to I minus. The radius is going up. That means the electrostatic forces are not as strong. Positive and negative cannot get close to each other as much. So with I being the highest radius, it's going to have the weakest forces and the lowest melting point and boiling point. I think I've discussed that before in my video. But then we look at the more challenging case on the left. We've got silver compounds, the same kind of halides, F minus, Cl minus, Br minus, and I minus attached to silver. Now, how is this going to explain the melting points here? 435 to 455 to 432 to 558. Generally, the trend is there's an increase as we go down to iodine, but it's kind of all over the place in the middle there, right? And this looks like potentially the opposite trend to the potassium halides, right? So why is this the case? The radius of the anion is still increasing as it goes down. So why is 558 the highest for silver? Well, this is where you have to consider, are these as much ionic bonding as the potassium ones? If you look at the electronegativity differences between silver and some of these halides, it starts to become questionably ionic. Certainly, many of these things are moving towards covalent bonding and more likely to be molecules instead. Like AgI has a low electronegativity difference relatively. So how does atomic radius affect covalent bonding? Not very much at all. It's more going to be determined by the intermolecular forces. Probably London forces are a big part of this one. So how is that affected by radius? Not much at all, but it's affected more by mass and size and number of electrons, which iodine has a lot of. That could explain its higher melting and boiling point. Okay, so we need a good way to figure this out when these kind of things happen and to what degree and what properties they will give. So 2.4.2, triangular bonding diagrams. We're going to really get into this. So here is a little screenshot of the triangular bonding diagram that you have in your chemistry, IB chemistry data book. Or if you don't have it, use my slide here. So this is a triangle with ionic on the top corner, covalent, pure covalent in the bottom right, and metallic in the bottom left. And you can see there's kind of regions that we're making a guess a little bit. These lines of triangles are a little bit arbitrary. But we should understand the axes. On the left, we have the electronegativity difference, delta X or delta chi. It's the difference of one material in the bonding minus the others, their electronegativity difference. Then on the bottom, on the x-axis, we have the average electronegativity. This would be just one of the atoms' electronegativity plus the other divided by 2. Or if you had 3 or 4 things bonding, you could add up all their electronegativities and divide it by the total number, I think. But usually we're dealing with 2. So, ionic versus metallic character. This is the vertical y-axis, vertical position. This depends on the electronegativity difference between the elements, delta X or delta chi. Metallic versus covalent character then is the horizontal, depends on the mean electronegativity between the elements, which is like X with a bar on the top, or chi bar, we could say. So you're going to want to find the position of your compound on this two-dimensional triangle plane. So let's see how that works. Practice 1. Consider the bonding structure of CF4, carbon tetrafluoride. Okay, so C, its electronegativity. If if you check in your data book, is equal to 2.6. F is the highest one. That electronegativity is 4.0. So when we check the difference, it's just 4 minus 2.6, that's 1.4. When you check the average, 2.6 plus 4 divided by 2, it's going to be about 3.3. So we just need to choose the correct axes, use these numbers as points, and find where we end up on the triangle. So I'm going to start with the x-axis first, x bar 3.3, and then delta x 1.4. It's going to put us right around here, almost on the edge. That's CF4. So that tells us that we're dealing with polar covalent. It is not a perfectly shared bond in terms of the electrons and electron density. Fluorine takes more, but these things have such high average electronegativity that they're going to be covalent bonding much more rather than any kind of metallic bonding. Okay, so that's polar covalent. All right, next, silicon. You still consider the difference in average even if you have only one thing, pure element. But what can we say? The difference is 0. You'll have Si minus Si, the same thing minus the same thing. The average, though, is just whatever it is in the data book for silicon. It's 1.9. So we go to our triangle. Delta x is 0, so we're going to be along the bottom edge of this triangle. 1.9 is right around here. Pure silicon, Si. So that is metallic, but it does have significant covalent character. It's on the right edge of this metallic triangle label. So you got to be kind of a little bit careful and vague about your wording here. It's metallic with some covalent character. And that means that it might be a little more brittle than other metals. It might be a little bit worse of a conductor. It's kind of in between the properties of metals and nonmetals, and that's what you would expect for a metalloid like silicon. Okay, BaI2, barium iodide. You can check the data for this. So barium, I think, is 0.9, iodine 2.7. So delta x is 1.8. And the average x bar is also 1.8. 0.9 plus 2.7 divided by 2. So we can plot that. Will be 1.8 on the x-axis, 1.8 on the y-axis. It's right around here. For barium iodide. So this is going to be ionic for sure. It's near this label. And you could say with a little metallic character, because it's closer to the left side of this triangle. It's still not really near the metallic label, but compared to the covalent side, it's much further left. Okay, sorry if that's hard to read. Ionic with a little metallic character, but still it's mostly going to have the properties of ionic compounds. Okay, so those are nice sort of spread out examples of covalent, metalloid or metallic, and ionic. Let's go next. Just more practice, that's mostly what we're doing today. 6 more. So CSF, cesium fluoride. We're going to have delta X be pretty huge, 3.2, X bar average being 2.4. So the average is really right in the middle, but the difference, 3.2, is like max. We're at the tip of this triangle. Okay, cesium fluoride is the classic ionic compound. We can basically say it's 100%. So it's going to have, brittleness, low conductivity as solid, good solubility, high melting boiling point. Next, F2, excuse me. Again, pure element, these are generally pretty easy. Delta X always 0. X bar average just equal to whatever it is on the periodic table. You should probably remember fluorine is 4.0. So that brings us to the other corner there. F2, the classic pure nonpolar covalent. Next interesting one, copper with zinc. This will be some kind of alloy, mixed metals. So delta X between copper and zinc, I think, is pretty low. Zinc 1.6, copper 1.9, so delta X 0.3. And then average will be right in between those, 1.75. So I think we're right around here. Copper zinc mixture. So that's going to be metallic, but with significant covalent character. Probably, yeah, kind of in the middle. Next, silicon dioxide, SiO2. Delta X is going to be 1.5. Silicon 1.9, oxygen 3.4, and then the average 2.65, I think. So that's going to put us 2.65, 1.5, right around here. SiO2. Polar covalent, pretty much in the middle of that, so it'll be a classic polar covalent compound. Next, Li2O, lithium oxide. So lithium is 1.0 electronegativity, oxygen 3.4, same as before. That gives us a difference, delta X of 2.4, should be right in the middle. And an average X bar 2.2. So that's going to put us in the ionic territory for sure. 2.4 up there, and then 2.2 here, somewhere around here. So pretty clearly ionic, probably slightly more metallic character than cesium fluoride, but still it's going to have the ionic properties that we know: brittle, high melting boiling point, low conductivity, crystal solid. And then AlCl3, this one I think is pretty interesting. So aluminum is 1.6, chlorine 3.2. That gives us delta X 1.6 and X bar 2.4. So where does that put us? Really in the middle of the whole triangle, not necessarily any specific section, but 2.4, 1.6 is right around here. Right on the edge between ionic and polar covalent. AlCl3. So this is basically going to have mixed properties of almost all three of these: covalent properties, ionic properties, and metallic properties, some mixture or in between of those properties. Okay, lots of good practice. Let's move on. So let's look at some mixed bonding type examples. Silicon is a good example. It's metallic and covalent. It's in the middle of that bottom line spectrum. So silicon is a metalloid, which is lustrous like a metal, but brittle instead of malleable. It's a semiconductor. Semiconductors have middling electrical conductivity, but this increases with some heat, light, or chemical impurities that excite the electrons in silicon. So all these things, heat, light, or chemical impurities, what they're doing is providing more electrons for conductivity. Heat and light can just help more silicon valence and outer electrons become more mobile and enter the delocalized C that would be in a metal. So I have a little animation here. You can see how that kind of happens. Okay, so you have a bunch of electrons in silicon. They're going to be in the valence orbital, the outer shell, not conducting very well. They need to pass through what's called a band gap into the conduction band. This is kind of the sea of delocalized electrons that are mobile and free to carry charge. So we'll first promote some of these up with some light or some heat. Once they get near the conduction band through the band gap, we can apply an electric field. They will be mobile and able to flow. And what happens is in the valence band that they left behind, there's now holes. Those holes, electrons can shift sort of left and right, lengthwise in between them, and also conduct electricity that way. But the holes will be moving in the opposite direction. Really, there's electrons also in the valence band moving in the same direction as the conduction band. I get that's a little bit hard to visualize. I'll show it once more. But if you also want to see a really good animation of this, check out Veritasium YouTube channel's video of blue LEDs. I think it shows it very well. These electrons moving in one direction, and these holes or positive gaps moving in the other direction in the valence band. This is how we're going to conduct in semiconductors. Okay, let's move on. Aluminum chloride, however, AlCl3, it has significant ionic and covalent character, but it has a much lower melting point. I showed it on one of my previous slides. Why is that? It can form dimers, Al2Cl6. This is two AlCl3 units stuck together. Instead of forming an expansive crystal that extends in all directions, they just stick together two, groups of two, and then as a kind of molecule, the material properties are determined then from intermolecular forces like London and whatever else. So let's see that. Al2Cl6 will happen when two AlCl3 molecules come together and form groups of two, dimers. And this can really happen because aluminum has an empty space, an empty p orbital, where chlorine a lone pair can donate and fill that up. And if both of them do this, one into each empty space on each aluminum in Al2Cl6, we get pretty strong dimerization forming of this molecule. A little animation here, maybe I can show that as well. So 2AlCl3 will come together. They're planar, trigonal planar. But when they come close enough, we can have chlorine donating some electrons into the empty spaces on aluminum. Now they have 4 electron domains on each aluminum. They're more of a tetrahedral structure. And this is kind of like a molecule. This will now be held together with intermolecular forces rather than being a large crystal structure. Pretty important. I think IB likes to use this example a lot. Okay, some more practice then. Outline the properties that a compound with the following bonding electronegativities would have. Electronegativity average 2.9, difference 1.4. This is going to be polar covalent if you go check out where that would be on the triangle diagram. Polar covalent. So we would predict brittle as a solid, low melting point, boiling point compared to other things, low conductivity, and possible solubility in water depending on its polarity. Would this be polar? Yeah, fairly polar. The electronegativity difference is 1.4 compared to, it could be 0 if it was a diatomic molecule. Solubility. So I would predict that this is probably soluble in water. Okay, B then, electronegativity average 1.9, difference 0.3. This is going to be metallic character. With covalent. Difference is so low it's not going to have ionic properties, but we can say medium conductivity, probably still high melting and boiling point if this is still a crystal lattice, which usually it is if it's on this line. Probably low solubility. And potentially brittle. But it's probably really in between brittle and malleable. I think we don't really know without doing further tests. So C then, average 2.3, difference 1.9. So this is going to be ionic. 2.3 is pretty in the middle. So I'll just say with some mixed character. So what properties is this going to have? It's tough to say, but we can go mostly ionic. So we can say brittle, low conductivity, possible solubility. Ionic are usually soluble, but as they get more covalent or metallic character, they become less. So we can't really say. And high melting boiling point, most likely. This is probably still a crystal. All right, so those are some brief outlines of how we would predict the properties of these things just based on the electronegativities of the atoms involved. All right, I think that's all I have for today. Next time we'll get into alloys and mixed metals and possibly polymers as well, long chains. So hope you learned something. Thanks for listening. See you next time.